Hello, this is my last video in a series of tutorial videos on resistor, capacitor, or RC circuits. If you watched the last video, then you are familiar with the idea of writing differential equations to model RC circuits and solving them to get the current and the charge across the capacitor as functions of time. And I did that in the last video for a simple RC series circuit that looked something like this. There was a DC voltage source with EMF, like that, capital epsilon, and a single resistor of resistance R, and a capacitor in series with that, with a capacitance that I just called C. And that was my circuit. There was also a switch here, or somewhere, it doesn't really matter where it is, of course, in the circuit. And we obtained some results for the current as a function of time and the voltage across the capacitor as a function of time, and consequently the charge on the capacitor as a function of time. Okay, and those results are all available in the last video. What I want to do now is look at a situation where a capacitor actually is already charged and then it's discharged across a secondary resistor. Okay, so let me, to model that, let me break this circuit here like so, and just so there's no ambiguity, I'm going to kind of break the ties on both sides here like that. Okay, and let's assume now that this capacitor was charged. So I had the switch closed and the current was allowed to last for long enough, to flow for long enough that the capacitor reached a full charge. And if that would be the case, then the charge on the capacitor must be, I'll just label it as Q sub C. So it would end up being the capacitance times the EMF of the battery. That would happen after a long time, right? Remember, the function for that was C times epsilon times 1 minus e to the negative t over RC, which, if you don't know where that comes from, you should watch the last video. Okay, so that time has passed. I've let t go to infinity, okay, and after a long time, t approaching infinity, this is the result that I wind up with. That is the charge on the capacitor. And so we're starting from that. The premise is the capacitor is fully charged, and we're starting at time 0 now. We're resetting time. Okay, so time 0 is now when the capacitor has that full charge on it. And instead of being connected to the battery and the resistor on the left, what I have here is some other resistor, right, which I'm just going to call this one, I guess we'll call this R. I don't know, let's call this one R prime, just so I don't have to keep using the annoying prime symbol in all the math I'm going to do from here going forward. So this is R, and that's R prime. All right, that doesn't affect this answer here. And I'm about to take this switch from my charged capacitor and close it so it's shut at time t equals 0. And then let's look at the transient behavior of this circuit. So what happens as the capacitor discharges? So first of all, I'm going to work under the model of conventional current flow. So that's the direction of the current. I goes in that direction. Now, if you use the PhET simulator from phet.colorado.edu that I used in my own videos a little while ago, you remember that they actually show negative current flowing in the other direction. So let's just kind of distinguish right now. I'm going to talk in terms of positive current flow, conventional current, even though we know that's not what really happens in copper wires anyway. That's not what happens. So the current's going to kind of go in this direction, and as it does so, these positive charges, imagine that they can move, would go back and neutralize and recombine with what we have on the other side of the capacitor. Because remember, when we have a charged capacitor, the capacitor itself doesn't have any excess charge on it. It simply has separated charge. So if there's, I don't know, 3 coulombs of positive charge on the top plate, then there's negative 3 coulombs of charge on the bottom plate. So the net charge on the capacitor still is 0, but it's simply polarized, separated. And so when you allow it to discharge, what you're allowing to have happen is those positives to come back around and meet the negatives, or wink, wink, really the negatives going back around to meet the positives. Okay, but in either case, we wind up with a scenario where there's no more charge left on that capacitor, no more separation of charge left on that capacitor once it's fully discharged. So how does that process go, and how does it look as a function of time? All right, so I'm going to do the same thing I did in the last video, which is to apply Kirchhoff's loop rule to this circuit. And I'm going to, for lack of a better choice, I'm just going to traverse the loop in this direction, even though I could certainly go in the other direction if I want to. And I'm going to start right there because I have to pick somewhere to start. And so the loop rule tells me that the voltage rise across the battery. Again, I'm moving from the no, actually there is no battery. Forgive me here. It's a capacitor. Yeah, of course. So here, let's erase that. Wrong symbol. So I'm going to start here at the bottom part of the capacitor, and I'm going to go in a clockwise fashion. So I will see a voltage rise, right? Because I've already established the fact that the positive side of the capacitor is here, the negative side is here. Right? And so in the previous video, when I was traversing this loop in this direction, I was seeing this as a voltage drop, V drop. So now, if I'm doing a loop in this direction here, I see that as a voltage rise. So I have the voltage across the capacitor, which I'm simply going to call V sub C here. That's plus. Right? We'll put that in to be explicit. And then the switch is closed already, right? So there's no voltage drop across that gap. Right? There's no resistance in that little segment of wire, so it's just nothing. R is 0, so I have no voltage. Here's the rest of my voltage drop right here. And so then I must have minus IR, essentially, right? That's the voltage drop across the resistor has to be equal to 0, like that. I wind up with that expression. That's it. And then in here, I can substitute, if I want to, Q, the charge on the capacitor, over C. Right, that simply comes from the equation Q equals C times V, or delta V, across the capacitor, V sub C in this case. Q over C equals I R, like that. Okay, and so now to actually solve for the transient behavior of the circuit, Q as a function of time, or I as a function of time, what I do is I simply define I over here as the rate of change of current with time, like so. But in fact, there's one more thing to consider, because here, in fact, in this circumstance, we have a situation where the current is related to the decrease in charge with time, not the increase in charge with time. So I actually have to consider that the current is equal to the negative rate of change of charge with respect to time. I is negative dq dt. That puts a minus sign back into this equation right here, okay, which we need actually to get the results to be meaningful. If we had left that out, the final results we would have obtained would have been ridiculous. I'll point that out when we get to the end. So here we have another differential equation that's much easier than the last one from the last video. And I can just rearrange this to read, let's solve it for dq dt, and that will be equal to negative q over rc, like that. And then rearranging that equation, I just get dq over q, right, keeping the left side as simple as I can, equals negative dt over rc. All right, and now I'm going to integrate that. I'm going to integrate both sides of that equation to get the solution that I'm looking for. And I'm trying to get q of t. That's the solution to this differential equation is a function, q of t. So I'm going to integrate the left side and the right side. And I'm going to think wisely about my limits of integration. In fact, in this case, I think I'll do this appropriately, right? So that the math types are happy with me. So I'll put in little primes on these variables here, and we'll integrate from a charge of Q naught, because that is where I start after all, right? That's my initial charge. Now we know what that charge is. We have that value. It's actually this over here, right? But we'll leave it as Q naught, to a final charge of Q, because I don't know what time I'm going to be looking at. It's not the final charge, which of course is 0, but it's the charge at some time. Similarly, my time is going to start at 0, and it's going to go to arbitrary time t right here. All right, so now I do the integration. On the left-hand side, I simply get the log of, here, let's go back to green. I get the log, the natural log, the ln of Q prime. Some people say, well, really, it's the absolute value of thereof. I'm like, I know that. I know that's the case. But in this context, it's not important for us. So I get the log of Q evaluated from, I should say, it has no significance in this particular instance. So I get the log of Q prime from Q naught to Q is equal to, and then here I simply get negative t over RC, okay, minus 0 when I plug that limit in. And kind of removing this natural log over here because I don't want to see it in the equation. I really want to solve for Q. I suppose I should plug in limits first, sorry. So I'm going to have the log, natural log of Q over Q naught, right, where I just skipped a step with the subtraction of logarithms, equal to negative t over RC, and then I can just use natural exponent base e and say e to the log of Q over Q naught. That's just going to give me Q over Q naught, like so, and that's going to be equal to negative t over RC, and then rearranging that, I simply find out that the charge as a function of time is equal to Q naught, initial charge e to the negative t over RC, like that, and then plugging back in what I know the initial charge to be from sort of before time 0, before the beginning of time, when I close the switch, was this thing over here. So I can put that back in, and I know that this is that, and I simply have, right, and it's, whether you use this or this, either of these is kind of debatable in this case, because this is particular to the fact that you know the initial charge to be equal to this value, which is predicated on the fact that this was charged previously in this particular circuit. This is a more generic equation that I think is actually more useful, because who knows what the initial charge on any given capacitor will be. But you can see that the charge decays exponentially with time. So if I were to make a graph of charge this time, first time, then that would decay like this. Typical exponential decay, just like when you have like radioactive decay or anything like that. All these examples that you see in your calculus class where they study this exact differential equation and the same scenario. It's just another example of exponential decay, and the charge does this asymptotically approaching 0. Now, if you want to know the current also as a function of time, then you just have to differentiate this, right? Because if you take the derivative of this, you can also wind up with an I of t equals, right? And go ahead and take your derivative, and you will wind up finding that it is also exponentially decaying, right? I think you can see that because the derivative of e to the negative t over RC is essentially e to the negative t over RC, and then the chain rule pulls out a factor of negative 1 over RC. And you go from there. All right. So that is the most important part, is being able to get to this point right here. So this is arguably a much easier example than when you have the charging scenario where you had the battery EMF to consider as well. This equation is much simpler to solve by direct separation and integration. And there you have the result right here. So, contrast this with the charging example from the last video. When we charged previously, the charge actually, the charge on the capacitor went up like this, and we were working under a function like this. This was the 1 minus e to the negative t over RC type of curve that was rising to some asymptotic value. Now we just have the charge across the capacitor decaying, as you would expect, down to 0. All right? All right, and then there's one more scenario that I want to look at, and I think I'll just kind of move over here, steal some space like this. And so this scenario is, well, what happens if you have not necessarily just charging or discharging in a simple circuit, but what happens if you go back to one of those examples that I did in a previous video where you have a circuit with some resistance here, right, like so, and then you have your capacitor, like so, and then you have a resistor here, right? How do you model that? What happens with these equations? What happens? So I'm going to give some labels to these. We'll call that R1, we'll call that R2, and we'll call that RC, and then this is just the battery. Again, no internal resistance to keep things simple, no resistance in the wires, so I'm just going to have the EMF of the battery be the voltage of the battery, the terminal voltage as you see it. And I want to derive some equations for the charge on this capacitor as a function of time and the current in this circuit as a function of time. You know, all the same stuff that I've just done. How do you go about doing that? Well, this is a two-loop circuit, right? So you might anticipate things are going to be a little harder. So if you start off, you can use the loop rule, but you have to pick the loop that you want to look at, right? So let's say that you determine, well, that's the loop that you want to focus on that loop. And if you're going to do so, you better pick currents, right? Kirchhoff law problems, you always have to wisely label your currents. So I'm going to call that I1 in that branch of the circuit. And then this is going to be called over here I2, and then this over here is going to be called I3, and that's my node or my junction right there, right? And I've chosen the currents as all kind of this clockwise fashion. That's reasonable, I believe, given the positive side of the battery is here. Right? Remember, it doesn't matter. You can choose your currents any direction you want, but I think I'll choose wisely in this case. And I immediately know that I1 is equal to I2 plus I3. That's the node rule or the junction rule from Kirchhoff, whatever you want to call it, right? We'll just get a couple different names. So we'll go junction rule. And that is probably something that's going to be important to me in this context right here. There we go, the junction rule. All right, now I'm going to start with my loops. So we'll do this orange loop first. And starting again at this location right here, I'm going to see a rise in voltage, the EMF of the battery, minus, I'm going from the positive side to the negative side of the resistor because I'm going with the current flow. So I'm going to see a minus I R1, but it's not just I, it's I1. Okay, and then I'm going to get to the battery or to the capacitor over here, right? And any voltage drop in this branch of the circuit has nothing to do with this current because there's no resistance in here anywhere. There's no IR. But I do have a voltage drop across the capacitor. So that's going to be Q over C, right? That's V across here. And then that's it. I'm done. I'm back to zero or I should say that all equals zero because I'm back to the terminal of the battery on the other side. So that's one equation. And I can simplify that just a little bit, or I don't know if it's a simplification, but I can make it just a little bit nicer. Well, you know what? Let's actually, no, scratch that. Instead, what I'm going to do, right, is change that first term. So this is going to be battery minus, let's see, can I do that? No, you know what? Let me leave it alone for now. I think this will be clearer if I leave it alone. Let's do the next loop. All right, so we can pick, we have a choice. We can either pick this loop here, or we can pick the outermost loop right here. I'm going to do the outer one. So scratch that right there. Let's do the outermost loop. Okay, so here we go. So according to Kirchhoff's law, we wind up with that minus, here we have another I1R1. That's good. Same resistor. Now over here, we have minus I3R2. That's kind of annoying that I have the 3 and the 2. I probably should have named these differently so that the 2 was with the 2 and so on and so forth, but we'll leave it alone. And that's it. I've traversed my loop, right? There's no more resistive elements or capacitive elements in between this point and this point. So if the wires are perfect, and they are, there's no more voltage drops, and I wind up with that equaling 0 like that. Okay? Okay, now, this is not going to be so easy to solve. And the reason being that I've got multiple currents in this case, right? And so what I would probably do at this point is take this I1 and plug it in for that. So that equation would then read, so instead of I1, I would have minus R1 times the quantity I2 plus I3 minus Q over C. You're wondering why I'm doing this, right? That second equation down here in green can stay alone. Now I'm going to rewrite this equation, minus R1. I2 stays alone, but I3, wait a minute, I3, actually no, this is a fault of my numbering system. I2 is the one I want to focus on at this point. So I2 is the current flowing into the capacitor and leaving the capacitor on the other side. And so that's the one that's related to the charge building up on the capacitor, right? That's what's physically charging and depositing charge on the plates of the capacitor. So I2 is actually dQ dt. And that's the point I was going to try to make a little bit earlier, but I think it's better to do it in this context. And then I have plus I3, and then I have minus Q over C equals 0. So I have this equation right here, right, which has, you know, dq dt, I3q. This looks like a differential equation, and it is, but it's got this obnoxious other current in it, I3. And I've got this equation over here, which has these two currents in it. Well, this situation is much more complicated than it was when I just had the series circuit, where I just had an R and a C, and that was it. Right? By putting this extra loop in here and allowing initially the current to go in both directions when I first close the switch, I've greatly complicated things. I have some kind of coupled equations here that make this a lot more difficult to solve, and so we're not gonna solve that. All right, I'm not going to go any further with that. And you're not responsible if you're taking an AP class, AP Physics C, E&M, or even an intro college level E&M course. You're not actually responsible usually for solving an equation like this all the way through to finish. But what you should be able to do is just intuitively think about what's happening at certain moments in time, when the switch is first closed, when the switch is first opened, and so on and so forth, right? I should say, though, that if you are the type of person that's interested in seeing things through to completion and you want to solve this particular system of equations, what I would encourage you to do is take this expression from the junction rule up here on the right and plug it in here so that you can eliminate I1 from this equation as well. And that way this equation down here in green would actually be in terms of I2 and I3. And then you know that I2 can be replaced by this quantity right here. I2 is really just dq dt for the capacitor. And so you'd wind up with both of these equations. This one down here and this one over here would be both in terms of dq dt and I3. And at that point you can go about whatever techniques you have of solving that system of coupled equations. It's interesting, and it's definitely solvable. It's worth doing, and it's an interesting exercise. So it's not something that you'd be required to do in an intro physics course. Certainly not at the AP high school level. More important, in fact, with a circuit like this, to understand the initial behavior of it when the switch is first closed and when it's open, or when it's opened later on, let's say. And in order to do that, you can watch a previous video. I talk about just conceptually how to know what happens using Ohm's law and the relationship for voltage across capacitors, but you should be able to intuitively do it without even having any of this mathematics. What happens when I first close the switch? Well, let's see. When the switch is first closed, this branch of the circuit in here has no resistance, so all the current flows that way, and nothing traverses this resistor just for that instant when the switch is first closed. So, boom, that tells you immediately I know what the current is in this circuit, in this branch anyway, because I've got the EMF of the battery and I've got that resistor, and that's enough. I've got my I, right? And I also know there's no charge across the capacitor yet. As time goes on, after a long time when the switch is closed, the capacitor will plug up and become a roadblock, so all of the current will simply traverse this outer loop, and I now have a series circuit with an R1 plus an R2 as my total resistance, and that's my voltage. Easy to get the current again. Okay. Once I have the current, I can tell you the voltage drop across this resistor. By knowing the current, I just calculate the V, the delta V across that resistor, and now I know the voltage drop across the capacitor because they're in parallel with each other. And if I know the voltage drop across the capacitor, I know the total charge on it. And so you can walk your way through the circuit knowing a lot about how it behaves. You just can't give me a value for the current or the charge on the capacitor at like arbitrary time. You won't be able to tell me Q of t at t equals 2 seconds or something like that. For that, you need the mathematics. You need to be able to solve this system to get the result. But again, it's not something that you truly have to be able to do in this circumstance. Okay, so I hope that this has been a series of 4 tutorials on RC circuits. I hope it was helpful. If you're in my class and you're watching these, there's some homework. You get a chance to practice and use all this stuff that you've seen here in that context with some actual AP problems to prepare you for the upcoming exam. So it's super important stuff. And if you're not in my class, I hope you're watching it. I hope it was at least mildly interesting. Take care. Bye.